So our next session is standardizing RAS, I'm going to read it wrong, RAS requirements for GPU and accelerators. And we've got 3 folks. I'll let them introduce themselves for the recording. And take it away, guys.
Hi, I'm Rama. I work at Microsoft. My focus is RAS at Hyperscale enablement.
I am David Newton. No, I'm not. I'm Sujoy Sen, standing in for David from Google.
Hi, this is Vishal Jain from NVIDIA. And with that said, shall we start? Cool. Thank you. Welcome, everybody. This is one of the 3 sessions we have in the series for enabling faster adaptations of GPUs and accelerators. As we have been listening in different talks and keynote speeches, AI has, we are seeing a tectonic shift in AI space. What it really means is to us as vendors that AI workloads need to take advantage of latest, greatest GPU technologies at the fastest pace. They cannot wait to put their hands on this gear, which what it means to hyperscalers is they need to integrate, test, validate, and operationalize their data centers to integrate GPUs, right? In order to do so, they need to left shift their development. They also need to make sure there is compatibility between the newer products and the data centers, the infrastructure they are running in their data centers. They also want to make sure that they are able to embrace products from multiple vendors all at same times, innovating at different point in the schedule, right? From NVIDIA perspective, we also want to ship GPUs to marketplace at speed of light, right? But working with hyperscalers, we figure out that there is no uniformity in requirements that come to us, right? Every hyperscaler has their own pet peeves, right? They want to do certain things differently for whatever reason they have, right? So back in 2022 Q4, Google, Microsoft, and NVIDIA, we came together so that we can harmonize the requirements that would help vendors to deliver products which meet the requirements rather than having design variations, right? So it increases the velocity from our side to get the products out, and it also helps hyperscalers to have predictable interfaces to integrate with. So they can prep their infrastructure by left shifting their development ahead of time before even the hardware shows up to them, right? So with that goal in mind, we created 3 work streams, right, under OCP CLA. One for firmware update standardization, the other is for RAS requirement standardization, and the third one is for GPU management interfaces standardization, right? This talk today, we're going to go in details with what we have covered so far with RAS requirements, and also the compliance tooling that we are proposing to tag team with requirements. Because what we have found out is just having requirements is not good enough. You need a common way to ratify a vendor implementations before it hits the hyperscaler doors. So having said that, I'll hand over the mic to Rama to take us through the details.
Yeah, hi, thank you, Vishal. Yeah, before I share some of the fleet learnings, I want to put a little bit of context in terms of the scale, current software resiliency techniques established already to handle this kind of hardware faults, okay? As you've seen from the keynote and other talks, right? The scale of systems we are talking about, tens of thousands GPUs until even maximum to 30,000 GPUs. That is the scale we are looking at. And second differentiation between compared to the CPU kind of workloads where there are multi-tenant. That means on CPU, there are multiple customers simultaneously with virtualization, right? The blast radius there is different, okay? In case of the super AI computer kind of designs, one single tenant occupying like few clusters, okay, spanning across hundreds of racks, okay? That is the scale you are looking at, okay? And in that scale of fleet, definitely the complexity of the systems, right? The one node has the CPU, motherboard, all the components, whatever you see in a server, then interface boards, then the GPU system, all that, okay? You scale that to like thousands of nodes, you see how many errors, the error rates can happen, right? And what is the current resiliency techniques they use, right? Because like we're proposing some RAS standardization to faster adoption of GPUs, but there is already some resiliency techniques in place. For example, checkpointing. How it works is the LLM models start training, okay? They frequently do the checkpoint of the state from CPU to the GPU state, okay? The end user can configure the checkpointing, okay? For like, generally they use like 15 to 30 minutes, okay? This is not used just for checkpointing, used for multiple purposes, not just for fault handling, okay? Like one of the recent published data, like just 1,000 GPUs, okay? If you run for 15 days, because of checkpointing, the LLM training model expands the training time by 20 to 30%. Okay, just at 1,000 scale of thing. The reason I'm telling that technique before I delve into the details is that even though there is a software resiliency techniques are there, but the impact in terms of TCO and operations, okay, adds the complexity to run this super AI computer for next 5 to 7 years, okay, at that scale, okay. We're trying to contribute some of the work of standardization, okay. First, we start with some of the learnings just related to hardware faults. First thing I mentioned is the service interruptions because of scale of the complexity, hardware faults you see, and that service interruptions leads to two critical things. One is like periodicity of checkpoint restoration. That means when the hardware fault error happens, based on the blast radius of the error, whether the error at the CPU level, GPU level, or interconnect switches, they'll use different checkpointing techniques to restore the state. The state restoration happens at node level or like a domain level, okay? That is we want to reduce the number of checkpointing needs, okay? To have a faster training time. That is the first thing. Second thing is the blast radius, right? Impact of a GPU HBM error, okay? If it is a fatal / uncorrectable errors, right? It can bring down the service impacts whatever the nodes of GPUs, like you may have 8 GPUs, it can bring down. But if there is a error at the, let's say, interconnects, between the nodes, there is interconnects, okay? If error happens, then it impacts the domain partition, okay? Think through the blast radius of the error, okay? And that can create. The third thing is impact-wise you see is number of nodes out of service. In terms of, you talk about the GPU count, each node can bring down tens of GPUs, okay? If this kind of things happens over the periodicity of the complex systems, you'll be losing the GPU devices. Those are the things we see, and there is a recent publications just on 1,000 GPU scale running for 2 weeks, it caused four interruptions related to hardware, okay? You see then at a scale of 30,000 GPUs, 16,000 GPUs clusters, how many interruptions you see, okay? Then once the nodes go to like repair state, how much time you take, okay, to mitigate the problem and bring down the GPUs into the service, okay? Whenever they want to bring down the service, they use the checkpointing as a time, okay? They run the diagnostics, then put into the service, right? That impact, the other thing is like to bring that GPU which is fallen or the system, other problems like IO, PCI switches, whatever happens, like you want to bring down, that means you need to have a precise telemetry, logs, okay, to identify the exact problem. Otherwise, what happens is, like, you may have second-time service interruption. Like, if the problem is, let's say, switch, you are trying to replace some other component, and repeat occurrence is the other problem we see at operating at scale. Okay, I don't want to go into other details. There is error containment to avoid the silent data corruptions. Okay, and also these errors can cause custom workload performance impact. If you have a storm of errors, or links, let's say PCI links get downgraded speed or width, right? You see the performance impact that increases the training times, okay? To put this all the problems, okay, and what is the scope of contribution, we'll go into that. Before that, I just want to give like little bit of context, just delving into GPU system. I know you're a CPU host CPU motherboard other kind of hardware is there, but we are standardizing across this GPU complexity, right? In typical GPU, you have the memory component called HBM, high bandwidth memory, like cache, like SMRAM, a lot of GPU cores, okay? Then you have a lot of I/O, like root port connected to the CPU host bridge, right? All that interface, okay? You have a lot of components, and that each block get repeated, like depends on the cluster, like super A computer size, like at thousands of nodes, okay? And then there is a platform level of problem, like this is called UBB, means universal baseboard. That's where you put this 8 OAM cards, okay? That can also have like a FPGA, PCI retimer issues. Those retimers can cause some hardware faults, okay? Then when you want to harvest this data, right, and take actions on whether error logs or some RAS features. RAS means reliability, availability, serviceability features. The silicon provides, the firmware provides. You take some actions on this data to manage that cluster. Some of the typical actions is run some field diag checks, predict errors before they happen using a correctable errors or temperature, okay? You set some rules on those, okay? And repair actions, right? This is the scale, there is an in-band interface and out-of-band interface. We are showing it here, okay? We went through the complex of the system complexity and the problems, working through this OCP CLA work stream. As Vishal mentioned, there are few contributions, I think Microsoft, Google keynotes mentioned this. Okay, one of the contribution is the RAS. We are contributing a 0.5 version. It was released 2 months before, and we are working also next version. We'll share more details what comes in that version. Okay, this is, I would say, we are still at early stages of things we can do. Okay, there is a lot of involvement working with vendors, a lot of SMEs over here, right, to improve this further. Okay, we are in the starting of this is the first spec release. The goals for the first spec is improve the node uptime, okay, serviceability, how do we service that using logs, analyzing the logs, okay. And the second thing is, I think in the previous talk, there's one question came up hey, you have a lot of this complexity in the systems, and even PCIe you get from multiple vendors, SSDs, networks, and GPU itself has a lot of complexity. How do we validate all this, right? If we see these problems after you go to the production, right? Like without validating, like that will be like not a bad sign operating at scale, right? One of the critical problem we discussed across the teams is like, what are the things we start with contribution? First thing is, how do we validate these flows, okay, across hardware, firmware, software stack? The validation requires tools. How do we inject errors, simulate the behavior of silicon, firmware, software drivers, GPU drivers, okay? And how do we validate that? Right now, if you want to validate, you get from like CPU vendor tools to do that, GPU vendor tools, I/O switch devices, interconnects. You get multiple tools from different vendors. And like you see the theme of this year, right? Scaling through collaboration. Like if you want to scale it, like all these tools to integrate, run the automation, right? It's a very complex job, right? That's why we do like a lot of automation, but integrating all the tools, like providing security checks and all, it's very complex, okay? That's why we are proposing some error injection-based standardization. How do we inject different type of errors, okay? Like that. Then the second one is serviceability point of view, is like error reporting, like how do we standardize that, okay? And the spec talks about a lot of details into implementation considerations, a lot of like out-of-band Redfish schemas, okay? And it gives you a lot of examples, okay? That is the coverage, around like 40 kind of page, current 0.5 spec, okay? That's what we are contributing. Just to, there is a lot of details. I'll just touch like few details into that, what is in the spec. The first thing I talked about error injection. We are choosing out of band, okay? For particular, we discussed about, hey, can we do in band, out of band, like which one we should choose. Like in band, there is already some standardization using like a ACPI, EANG methods, okay? Problem is that ACPI is mostly covered in the CPU space. GPU space, like that is not the standardization. Second thing about think through the node life cycle, right? Node goes through, before it lands in the production, it goes through SKU development phase, manufacturing stage, and then pre-cluster testing, right? We want to make sure that the tools work in every environment. Each environment may have a custom OSS, like different versions of OSS, maintenance OSS, manufacturing. We didn't go through in-band approach. That is the reason, like the environments will change. You will say like this version of the OS, that version of the OS, whether you're in SRIO mode or like different GPU operating modes. Okay, we choose the out-of-band. In the out-of-band, like we describe the APIs and schemas to inject different errors. You have seen that memory, I/O devices, GPU internal errors, interconnects, right? In the 0.5 spec, we discuss about memory and PCIe, okay? Inject like correctable errors, uncorrectable errors. Okay, similar thing with PCIe system, okay? The details of the each error types, Redfish schemas, that is the one of the contribution in this area, okay? And the key summary of this is, we are trying to validate all the complexities which can happen at scale, trying to make sure that hardware, firmware, software stacks are working as expected. Okay, that is the first theme. Okay, second theme of the 0.5 version spec is like when errors happens at scale, like how do we harvest this data? How do we automate processing these logs, right? We want a very like automated way, less manual interaction, all the actions to identify either you're replacing a particular fru. How do we identify that? Okay, or you may find the mitigation through software, firmware, or a solution, right? For all that, but you need a rich set of logs, right? We talked about the impact of that is like if nodes not in service, like which are very costly GPUs, right? If we improve the richness of data And processing of the data, the tools, I think we are leveraging like existing standards, previous OCP contributions, like for CPU, there is a work done standardization. We are using that CPER format called Common Platform Error Record. It comes from UFI specification. Then actually last year we worked with Jeff Other because the DMTF has some, that time, like there are some improvements required for hardware faults. We worked with the Redfish team, with the OCP and DMTF collaboration, and there is some improvements done in that area. We are using that work, leveraging that work, okay? And how do we do it for GPU devices? Okay, first is error reporting, okay? The advantage of that, there is a processing tools of that records is already exists. You just need to improve on like for the devices. Second thing we are standardizing on, like just getting the error details, you may not know full root cause of it. Second thing we are doing is system debug dumps or crash dumps you might have heard in the CPU world, right? And on GPU complex systems, you have multiple retimer dumps, IO switch, LTSMM states, GPU internal HBM. All this requires some debug dump data collection. If I'm trying to do the debug dumps, different types, different formats, how do I process them? That is the one of the area we are standardizing that, okay? Like what formats the debug dumps should be there, how easy to process, what are the analyzer tool requirements, because the tools we get, right, we want to depend on the silicon vendors, like they know exactly what data to put. There are so many vendors in the total system. We want to get that. That is also work leverage from our like other work stream we lead is the OCP hardware fault management. Okay, we are leveraging that work. This RAS is part, RAS, GPU, RAS management is part of that work stream. We're not reinventing the wheel. We are trying to leverage the previous last year contributions. How do we mix them with GPUs, okay? That's where we are doing the standardization. Okay, I'll give it to Sujai to go through the next details.
Thanks, Rama. So I think Vishal mentioned this. One of the unique things I think we are trying to do here is for all these three work streams around GPU manageability is to come up with create a sort of a compliance tool that will be a companion to the spec. So all the specs that we write. And so this will allow not only just the vendors to ensure that their implementation is spec compliant, it will allow the hyperscalers to when they get the part in to make sure that it's actually compliant. System integrators can also do the same thing. And it leverages this OCP's test and validation framework. It's extended it a little bit, and it's very flexible. So we're going to have a demo of this in the 350 session, on the firmware update session. The firmware update part of it is probably the most developed right now. There's a lot of code in the GitHub location, and the links in there. And then there's some implementation for the manageability interface as well, and that'll be followed by RAS. So now that we have a 0.5 version out that Rama sort of went through, our next step is to get a 0.7 version out. And that'll be comprising of a few things. One is get sort of wider feedback from the fault management group, working group, as well as working through defining some of the details around the GPU crash debug dump. And we are planning to publish it in November, and then eventually get to a 1.0, which would be further alignment with OCP hardware fault management, sub-projects, make sure it meets all those requirements, and spend a little bit more effort in how to standardize and harden the software stacks for these GPUs when it comes to PCI error resiliency, not just from a hardware point of view. And then serviceability, as Rama mentioned, is a big one, right? So and that requires failure analysis to be as accurate as it can be. So that's going to be a focus for the 1.0 version. And the compliance tool, like I said, we will add all of the RAS specification tests in there as well, and release it at the same time. So we have a few email aliases as well as group discussions where we welcome feedback. And if you'd like to contribute and join this particular work stream or any of the other 2 work streams, you can definitely contact us, and we'll include you as part of the CLA. And with that, I think maybe we have time for a little bit of Q&A. Okay.
Maybe a question to Vishal. So GPU, given now it's in the main line for accelerated compute, how do you see the RAS of it being divergent from like the CPU RAS, which also has the same memory components, as well as like GPU will become the compute in a way, right? So can we piggyback on some of the RAS things around the CPU, which are already kind of mature in a way? And the second aspect is with respect to PCI SIG, that we talked a lot about out-of-band error reporting, but the SIG doesn't mandate any shadow representation. So there's always a in-band path which gets accessed by OS, but PCI SIG doesn't mandate there has to be a shadow which would be accessed with out-of-band. So how a race condition where both are kind of simultaneously accessing the endpoint can be managed?
Right. No, thanks for that question. I'll take the second one first because it's hard to deal with. Okay. So yes, definitely, we are talking through those, ramifications of those out-of-band requirements. So right now, error propagation is primarily through in-band, and there is some sort of notification going on out-of-band route. What we are talking about here is making those notifications standard, right? We don't need to have NVIDIA specific or AMD specific or somebody else specific mechanism for those notifications. So at least post-processing of those notifications and remediation actions can be clearly, crafted ahead of time before the product, hits the door, right? But we still have to, until self-recovery kind of a thing is embedded in the device itself, I think we'll have to, out-of-band will have some laggard behavior with respect to in-band, right? Now going back to your first question, whether we can leverage RAS capabilities of CPU and GPU, right? I think although the primitives are same, but notification mechanisms are way different, right? In x86 land, where everything has to propagate as a PCIe construct, right? Or as an MSI mechanism, right? Which is massively different from how we do x86 error handling, right? So I think as long as we can, as GPU and accelerator vendors, we can harmonize on notification mechanisms and standardize the payload, I think we should be in better shape.
Just to add one small point is like, we're talking about GPU, like the PCIe, still requires like resiliency features, or like, so for example, EDPC, right? Resiliency feature still requires a GPU driver stack, the in-band, even the poison errors. That we are not changing, right? You cannot do that through out-of-band, right? Where even some errors, like say PCI AER, is mostly like you mentioned, like in-band. We are enriching that. Those are already standardized through CPR and all that. The processing tools already there, okay? We don't want to, whatever is like already standardized, we don't want to touch that. We're trying to fill the gaps where they're not there.
All right, no more questions. Right, thanks, guys. Thank you very much.
Thank you.